Today's numerical is a circular rod 120 mm diameter and 500 mm long is subjected to a tensile load of 1000 kilonewton. Determine modulus of rigidity, bulk modulus and change in volume. Assume Poisson's ratio 0.3 and E is equal to 2 into 10 raised to 11 Pa. First step is understand problem. Then for that problem draw drawing circular rod of 120 mm diameter. This is diameter denoted by capital D and 500 mm long. This longitudinal length of this bar or rod is denoted as L, is subjected to a tensile load of 1000 kilonewton. This tensile load P determine modulus of rigidity. Modulus of rigidity is capital G, bulk modulus is capital K and change in volume. Modulus of rigidity is shear stress to the shear strain and bulk modulus is volumetric stress to the volumetric strain. Given data, diameter of rod D is equal to 120 mm, length of that rod 500 mm, subjected to a tensile load of 1000 kilonewton. P is equal to 1000 kilonewton. That means 1000 into 10 raised to 3 Newton. 1 kilonewton is equal to 10 raised to 3 Newton. That means 1000 kilonewton is equal to 1000 into 10 raised to 3 Newton. Determine modulus of rigidity, bulk modulus, change in volume. Assume Poisson's ratio mu is equal to 0.3. Poisson's ratio is lateral strain to the longitudinal strain, and for that rod material Poisson's ratio is 0.3. Young's modulus or modulus of rigidity is stress upon strain and is 2 into 10 raised to 11 Pa. See, this is in Newton. This unit, this load unit is in Newton. Length unit is also in mm and diameter unit is in mm. But here Young's modulus unit is Pascal. We need this Young's modulus unit is in MPa or Newton per mm square. For that, see here 1 Pascal is equal to 1 Newton per meter square. But we need this Pascal unit is in Newton per mm square. So here for Newton per mm square, see here 1 upon meter, convert it into mm. 1 meter is equal to 10 raised to 3 mm and this square mm square. Therefore 1 Pascal is equal to 1 upon 10 raised to 6 Newton per mm square, and 1 Pascal is equal to 10 raised to minus 6. This 6 10 raised to 6 goes to numerator, 10 raised to minus 6 Newton per mm square. Therefore here Young's modulus 2 into 10 raised to 11 into 10 raised to minus 6 Newton per mm square, and 2 into 10 raised to 5 Newton per mm square. C. This Young's modulus or modulus of elasticity is 2 into 10 raised to 5 Newton per mm square. And still Young's modulus is 2 into 10 raised to 5 Newton per mm square. Here in numerical question they don't write or type which material which material for this circular rod, but by the sense of this Young's modulus of steel is 2 into 10 raised to 5 Newton per mm square. That means this is steel circular rod. By seeing this Young's modulus, we get sense of this which type of this which material of this rectangular bar is. Now next, to find first shear modulus G, second bulk modulus K, and third change in volume delta V. Solution: C. For finding this shear modulus, what data we have? First, see what data we have. Second, see what we have to find. And by using what data we have, what we have to find, by using their relationship, find which formula is effective for finding the shear modulus. See here, E. E is available here. E is equal to 2 into 10 raised to 5 Newton per mm square. mu is also available 0.3, and remember there is one formula, there is relationship between E, G and mu, relationship between Young's modulus, shear modulus and mu. So use this formula. Using relation between E, G and mu, E is equal to 2G in bracket 1 plus Poisson's ratio. We derived this equation already in one of our previous lecture. E is equal to 2G multiplied by 1 plus mu. Therefore, this G is equal to, shear modulus is equal to E upon 2 in bracket 1 plus mu. G is equal to, E is 2 into 10 raised to 5 upon, it's 2 into 10 raised to 5, 2 into 1 plus mu. Mu is 0.3. Yes, 0.3. Therefore, here shear modulus is 2 into 10 raised to 5 upon 2 into in bracket 1 plus 0.3 is 76.923 into 10 raised to 3 MPa. That means approximately 77 into 10 raised to 3 MPa. And here Young's modulus is 200 into 10 raised to 3 MPa, and shear modulus is 77 into 10 raised to 3 MPa. Young's modulus generally always greater than this shear modulus. That means this is checkpoint here. Check our answer is correct or not. This shear modulus is less required to be less than this Young's modulus. Okay. Now next we have to find bulk modulus K. See, for finding bulk modulus, use relationship between Young's modulus, bulk modulus and Poisson's ratio. We have Young's modulus, Poisson's ratio and bulk modulus relation. Now use this relation. This relation is also derived in our past previous lectures using relation between E is equal to 3k 1 minus 2 mu. Therefore, k is equal to E upon 3 in bracket 1 minus 2 mu. E is 2 into 10 raised to 5 upon 3 in bracket 1 minus 2 into 0.3 Poisson's ratio, and therefore this k is 166.67 into 10 raised to 3 MPa. And this k is in between this Young's modulus and shear modulus. This k is yes, in between Young's modulus and shear modulus. That means greatest value is this Young's modulus, after that this bulk modulus, and after that this shear modulus. Shear modulus is lesser value between k and E is bigger value. Okay, this is bulk modulus. Volumetric stress to the volumetric strain. This is shear modulus, shear stress to the shear strain, and unit is MPa. Now next find change in volume. For change in volume, first volumetric strain EV is equal to change in volume. EV is equal to here change in volume to the original volume, delta V to the V. Okay, and we also derive one derivation. Remember one of our past lecture, bar subjected to uniaxial stresses. In that derivation, we calculate EV formula. EV is equal to EV. This EV is E in bracket 1 minus 2 mu is equal to change in volume to the original volume, and this E is nothing but the stress to the Young's modulus. And our objective of this step is delta V, calculation of change in volume. Put this stress value, Young's modulus value, Poisson's ratio value and volume of this circular bar. This okay. Delta V is equal to stress is load upon area. You are right. Stress is load upon area. I put this stress is load upon area P by A into A into 1 minus 2 mu into volume. This P is 1000 into 10 raised to 3. divided by area is pi by 4 into 120 square multiply by E is 2 into 10 raised to 5 multiply by this 1 minus 2 into 0.3 multiply by this V is, see here, volume, which is, what is this V? Okay, volume is area, volume of that, see this rod is cylindrical and volume of the cylindrical rod is area into length, A into L. Simply volume for that rod is area into length. Their area is pi by 4 into 120 square into length is this 500 mm. After calculation of this, change in volume is calculate 2 into 0.3, 0.61 minus 0.6, 0.4, 1000 into 10 raised to 3 into 0.4. That means 400, 1, 2, 3 multiply by pi by 4 into 120 square into 500. 565486 6.78 divided by pi by 4 into 120 square into 2 into 10 raised to 5 22619 46711. This is change in volume. 4 1 2 3 4 5 multiply by 5654 866.78 divided by 22619 46711 1000 mm cube. Unit of this change in volume is 1000 mm cube. See, a circular rod of 120 mm diameter and 500 mm long is subjected to a tensile load of 1000 kN. Determine modulus of rigidity G, bulk modulus K, and change in volume delta V, and assume Poisson's ratio mu is 0.3 and Young's modulus is 2 into 10 raised to 11 Pascal. We first understand this numerical. After understanding this numerical, we draw diagram of that circular rod. This is given data for this circular rod, diameter D120, length 500 mm, load acting, tensile load acting 1000 into 10 raised to 3 Newton, mu is 0.3, Young's modulus is 2 into 10 raised to 5 Newton per mm square. That means this is steel rod. 1 Pascal is equal to 10 raised to minus 6 Newton per mm square. See solving step for this numerical. First we use using relationship between Eg and mu. E is equal to 2G in bracket 1 plus mu. And by using this formula we find shear modulus. Shear modulus is shear stress upon shear strain. Next we have to find bulk modulus. By using this relation E is equal to 3K into 1 minus 2 mu. We find bulk modulus is 166.67 into 10 raised to 3 MPa. And change in volume is 1000 mm cube. original volume of this circular steel rod is pi by 4 into 120 square. That means 11,310 mm cube, and change in volume is 1000 mm cube. Young's modulus is 2 into 10 raised to 5. Shear modulus is lowest value come between this Young's modulus, shear modulus and K. This shear modulus is lowest value, Young's modulus is highest value, and this K bulk modulus is in between this value. Thank you very much.